Good morning, everybody.
Good morning, ma'am.
Okay, 32 have already joined, so let us start while others join in. So we are going to continue with our matrix multiplication problem by doing one more example, and then we'll move to a different example of dynamic programming. Okay, so we were going through the matrix multiplication algorithm yesterday. So let's go over it again. So what you have to do is you have to find, because we are using a bottom-up approach, we first find the number of multiplications required for every pair of matrix in the chain. Then we do the same, we find the minimum number of multiplications for uh, let's say 3 matrices in the chain. So we are increasing the length of the chain. So our goal is to find the minimum number of multiplications for a matrix chain of length n. So we are starting from length 0, then length 1. Then length 1 means 1 matrix, so there's no multiplication, it is 0. Length 2 is 2 matrices, all the pairs in order that you can multiply. We find the number of minimum multiplications for that. For 2, there's only one possibility. Then we increase the chain length to 3, and we take 3 at a time in order. You can think of it like a window which has 3, and then you slide the window one by one. So for all the possible 3 pairs in order, we calculate the minimum number of multiplications. So that is done here in your loops. So if you see, this is the length. So while the length of the chain is 2 to n, so we start with the lowest length chain and we go up to the final length, which is n. So we do the calculations. So these are the ij values. We saw how the ij values, j is I plus 1. So here they use the formula n minus l plus 1, I plus l minus 1. It is the same thing. You can just check with some values. We initialize all the elements of this 2D array mij as infinity because we are trying to find a minimum. So the first time you compare the value you calculated with infinity, obviously your value is smaller, so that will be put. If there is another way of multiplication, that will be taken care of here. So your k ranges from I to j. So for all the values k can take, we do this calculation here, this formula, and we see if what we calculated is smaller than what is existing in this step, and then whatever is smaller is put inside. We also put the k value for which we got the least number of multiplications, this last line, in a separate table, in a separate 2D array, which is named S. Okay, I'll show you by an example how it helps us to find the actual parentheses. Okay, let's first take an example. You have a chain of 4 matrices with the orders are given. So P0, P1, P2, P3 is given. So you have first matrix of order 5 cross 4. Second is 4 cross 6. Third is 6 cross 2, and fourth is 2 cross 7. Okay, these 4 matrices in order are to be multiplied. We have to find the minimum number of multiplications. So that will be stored in M14 because your chain goes from 1 to 4. This is 1 to n for us. Okay. So what you see here is, if you remember yesterday, we said that we have to calculate in the matrix. We have to calculate this upper part, the one that I'm shading red. So this is the only part that in the 2D array that we have to calculate. So they've just done like this. So this is the part that we are calculating. Just flip the matrix in the form of a triangle. This we don't calculate, so there's nothing under this. So what you see here is just the upper triangular matrix. It's the same thing, just the presentation is different. And they have written the order of the matrices here. Okay, so when you have to multiply uh, the first and the second matrix, you will use P0, P1, and P2, and that answer will come here. We'll see the calculations. Okay, so this is the same 2D matrix, just it is just tilted pointing upwards so that it is the upper triangular matrix. So initially, what you have here, basically this box is 1 1 in this array, 1 and 1. So when you if you have a chain of length 1, the number of multiplications is 0. That is the initial case of our formula. So if you see here, we have done that initialization here. All the MII are set to 0 because when you have chain of length 1, the number of multiplications required is 0. So that is already initialized here. Now what we have to do is we have to calculate the pairs. So the pairs are calculated diagonally, so that will be like this in this case. So 1 2 2 3 3 1 2 2 3 and 3 4. Okay, so first we will calculate M12. So you have to apply the formula. M12 is a chain of length 2. So there's only one possible way of multiplying. We don't have to find a minimum, because if you see the k values, they range from k can be greater than or equal to 1 and less than 2. So there's only one possible value, which is 1. So M11, M22. So it's just this will be 0 and this will be 0. So you're just multiplying P0, P1, P2, which is the order. Okay, and you get 120. You put it here at the first location. Next we have to calculate this is 2 3. Okay, so 2 3, again the k values, they range from 2, it can be equal to 2 but less than 3, so only one possible value. Again, it is just multiplying two matrices. So this is 0, this is 0, and this is P1, P2, P3. Whatever your answer is, put here. Similarly, again, a pair of matrices multiplied together, k can take only value 3. So M33 is 0, 44 is 0, and this is the actual calculated from the order of the matrices, and you get 84. So once you have all the pairs ready, now we will go for length 3 matrix chain. So the next entry is this is 1 3. So the chain is of length 1 2 3, length is 3. So when you have length 3, for example, you have A, B, C, there are two possible ways of multiplying them, right? These are the only two possible ways. So you have to do both the calculations and you have to find the minimum. And how that is taken care of, this k is this point. This can be 1 or it can be 2. So you can put your first division at 1, that will be this case, or at 2, that will be this case. So k, the chain is of length 3, I and j is 1 and 3. So k can be 1 and k can be 2. Okay, so based on that, if you apply this formula 1 1 and k plus 1 3 2 3 and this. So 1 1, it is 0. Here 3 3, it is 0. 2 3 you will get from the table, which is 48 and this value. So based on this, the value you get here is 88. This 88 comes from, let's see, 2 3 is 48 and 1 2 is 120. Obviously the answer is coming from the first one because you have 120 here. So that means k is equal to 1. Okay. So we have not stored k yet somewhere. So what we do generally, let me draw that on the whiteboard simultaneously. So we have this This you can say this is the S matrix to store the S values. So when you multiply one A1 and A2, there's only one way of multiplication. So A1 and A2, your K value is here, that is 1. 2 and 3, it is 2. 3 and 4, it is 3. Now, in your problem that we are doing, we got K value as, in the chain 1 to 3, we got K value as 1. So we will put that here. This is your S table or your Sij. So we are calculating for 1, 3, we got 1 here. Okay, so let's go back. So similarly, we will go to calculate the second chain of length 3, which is 2, 4. So 2, 4, K can take values 2 and 3. So here you see M22 is 0, M44 is 0, M34 is 84. Did we miss something? Yeah, no. So 84 and 2, 3 is 48. Okay, the answer is 104. So I think P1, P2, P4. Let's check what is P1, P2, P4. P1, P2, P4 is 24 into 7, 188, and this one. P1, P3, P4 is P1, P3, P4. 56. Okay, so this is 56. So this 104 comes when K is equal to 3. So our K is 3 in this case. We'll just fill it up here on our whiteboard. We'll put 3 here. Okay, so in the chain of length, when you're multiplying A2, A3, A4, yeah, this is where you split. Okay, let's go back and do the final one. Now, what is the final chain? 1 to 4. So 1 to 4, K can take values 1, 2, and 3. So taking all of these, you apply the formula. There are three calculations you have to do. 1, 1, 2, 4, 1, 2, 3, 4, 1, 3, 3, 4, 4. So the answer is 158. Okay. So I don't know where it is coming from. 158. So they haven't written the K value, I guess. Okay, let's do the calculations. I just use the whiteboard for that. Let me first copy the values on. Okay, let me. So P0 is 5, P1 is 4, P2 is 6, and P3 is 2. So how it is split. Okay, let's go to the whiteboard. Just give me a second. So we'll do the calculations. If you have been given, you have the table in front of you, you can use paper and pen. That's what I'm doing so that I can find the K value. Okay, so M11 is 0, M24 is 104, and P0, P1, P4 is 20. P4 is 7. P0, P1, P4 is 140. So K equal to 1 is not possible. That gives a bigger value. 1, 2 is 120 plus 3, 4 is 104. Again, that's not possible. So probably K is 3. 1, 3 is 88. 4, 4 is 0. And P0, P3 is 10, 70, 158. Yes. So K, your K is 3. Okay. So if you see on the whiteboard, let's put K equal to 3 for 1, 4. So what does this S table tell you? Now I'll write the chain of matrix here. Let me erase this. Okay, this is the S matrix that I have got. Now I have to read this table. So if you have to print to the user the output of the program, which will be the order in which you will tell the user to multiply the matrices. Where will you get the order from? You found the minimum number of multiplications, which is 158, but you haven't yet found which order. So the order is stored in this table. So how do you read that? So what is the chain length? The solution, oh, sorry. The solution that is stored, the minimum number of multiplications are found in the column 1, 4. So you go at 1, 4, you see that K is equal to 3. So this is how you will put your first bracket, because the K is at 3. So that's the split. Now your split gives you two chains. One is of length 1 and one is of length 3. Okay. What is the chain? The chain is A1 to A3. So you go to 1 and 3. Okay. And you find the next entry. What is the entry there? That is 1. So that means the next split is here. So it's going to be like this. Okay. Now what is the chain that is left here? A1 and A23. So A23, if you go and check what is A23, that is 2. Means this is where the division is. So it's a pair, so you don't need to worry. There's just one way of multiplying. So A1, A2, A3, A4, this is the parenthesis. I'll just write the orders of these matrices here. 5, 4, 4, 5, 4, 4, 6, 6, 2, and 2, 7. So these are the 4 orders. Now, based on what the parenthesis we read from the S table, let's multiply 2 and 3 first. The number of multiplications is 4 into 6 into 2. Okay, then they are, according to this, we have to multiply A1 with this. So when you multiply A1 with this, the final order will be 4 cross 2. So the number of multiplications will be 5 into 4 into 2. So now this part is complete. What will be the final order of this matrix? 5 into 2. So 5 into 2 into 7. Okay, that is this 7. So what do you get? 12 fours, 48, 40, and 70, add them up, you get 158. So you are getting the minimum number of multiplications. So this parenthesis is correct. Okay. We'll see one more example in the slides. So this is how, so side by side, when you are writing down or filling up your M table, you also fill up your S table with the value of K, which gives you the least number of multiplications. Okay. Now this is how you first maintain another 2D array. You are taking up some extra space, but that is giving you the solution. Though it talks about the same thing. So you, for that sequence, you split at whatever location it tells you, and then you find the K values for each of the two chains separately. So for example, if you had a chain of length 6, if it says here S16 is 3, that means the first split is at 3. Then there are two chains 1 to 3 and 4 to 6. For 1 to 3, it says the split is at 1. So they have put here. And for 4 to 6, it says the split is at 5. So this is how it is going to be. So overall, you will get this. So you read the table, the first K value will be the first place where you have to parenthesize. Okay. So this is again the same problem, the dynamic programming algorithm for matrix chain. So what we are doing is we are adding this additional step here to save the K value for which Q was the minimum. So again, what is the runtime of this algo? This for loop is a separate for loop. It just initializes all the values to 0. There is a nested for loop. There are 3 for loops. Maximum runtime can be n. So n cube is the runtime for this. So again, an example of Sij. I just moved to the example. If this is the S table that has been formed, and you have the chain A1 to A6. Okay. Now, what is the, in 1-6, you are reading the value 3. That means the first split is at 3. So you will now get two chains, 1 to 3 and 4 to 6. Okay. For 1 to 3, you go and check 1, 3, you find 1 here. So you are getting two chains, 1, 1 and 2, 3. This is only for this part. For the other part, 4 to 6, you get 5 in the table. So 4 to 6 is 4, 5 and 6, 6. So if you have to so first split is here. Okay, for 1, 3, the split is at 1. For 4 to 6, the split is at, it's actually like this, and then like this. So this will be your final parenthesis. You can also print the output. It's just a small function which does that. You print A and you print, this is the recursive call. There's some example here. So if you're passing A16, then if I is 1 and J is 6, you call pop S13 based on the S value, and this will further call 2, 3 and 1, 1, and it will print the output. This is a very small program. You can try writing this. Declare a 2D array, declare a P array for storing the orders, and you have to declare two 2D arrays. One is M and one is N. Write this program with this formula. That's all. This is all the code you would need, and then add this in the end so that this helps you see the answer like this. So, okay, so that is your matrix chain multiplication. another example. Okay, you have any questions? You can ask. If you saw in yesterday's lecture, if you do it with a simple algorithm, it gives you an order of the order of 4 to the power n, omega of 4 to the power n. The way we are optimizing, even if you use simple recursion to solve any problem, we have repetitive subproblems. We are eliminating the need to solve the same problem again and again. Okay, so all different chains can lead to, will break down into chains of length 1 and 2. If we already know which one is least, then we can use that in the longer chain. So that's why it is bottom up. N cube is a bad time, normally speaking, but then for matrix multiplication, it is the best time you can get. Okay. And normally when you are asked to do matrix multiplication, the problem is not multiplying. The problem is the different, finding the best way of multiplying. So that is why it is an optimization problem. Because what is the best way of multiplying? That will use the least number of multiplications. And that is why our matrix multiplication is a minimization problem. We minimize the number of multiplications, and that is basically that is where the optimization comes. Clear? Yes or no? And Mij is 0 for all I equal to j, because when you, what is M11? It is multiplying A1 with A1. You're not actually multiplying. There is, when you have chain of length 1, I equal to j means chain of length 1. You are not actually multiplying, so there are no multiplications required. When I and j differ by 1, that means there are two matrices and you are multiplying them. It is simple. Finding from the order, you can calculate the number of multiplications. The actual minimization comes when you go to chain of length 3, because then there are two ways of multiplying. So you have to find minimum of the two. When you go to chain of length 4, there are how many ways? Yeah, 3 ways of multiplying. So you have to find minimum of 3. As the chain length will increase, the number of possibilities will increase, and you have to find minimum of all of them. Okay, you want to take another example of matrix multiplication? I think I'll give you one more example to do on your own, so that this becomes a little more clear in your assignment, which I'll give you this weekend. I'll give you a couple of assignments. It's just that I am not able to make one this time. I think one more example you will do, and if you have any questions, then, because I already did two, if you have any questions, then we can repeat it. Okay, so once you sit down and do it mathematically, it will be much more clear. Okay, we will do another example of dynamic programming, similar one, but the problem that is at hand is different this time. Okay, so the next problem that we are dealing with is the zero, it's known as the 0-1 knapsack problem. Okay, so what is the problem? The problem is described like this. It can be applicable in many different scenarios, but the simplest one that we do for understanding is this problem of a thief entering a house. The thief is carrying a knapsack which can hold only up to a particular weight. So that weight is W. This is, I have typed it wrong. There are n items present in the house, okay, in the first line here. There are n items in the house. Every item is associated with a weight because and it has a value. So the thief is carrying a knapsack which can hold a weight of W. This is capital W. So every item has its own weight Wi and its own value Vi. Okay, and the total capacity of the knapsack the thief is carrying is W. Okay, so now the thief has entered the house. His aim is to get the it's not to collect the maximum number of items. The aim is to collect the items in such a way that he can maximize the profit he gets. That is the value of all the items. Obviously he has a weight restriction. He cannot pick up everything, so he has to pick up selected items, and those selected items should be within the sum of the weights of those items should be less than or equal to this capital W, and the value should be maximum. So he has a restriction of weight. That's why he cannot just pick up all the items. So whichever items he decides to pick, it has to be picked up such that he will get the maximum value and also be within the weight limit of his knapsack. Okay, so let's say the bag he's carrying has 20 kg weight, possibly can carry 20 kg weight. You can see there are 6 items. Every item has a weight and a value. So let's say this item has weight 4 and value 6, again 4 and value 7, 2 and value 4, and so on. Now, before going ahead, why is this problem called a 0-1 problem? There are two versions of this problem. One version is this 0-1. It is known as 0-1 problem because the thief has the choice to pick or to leave the item. So there is no way he can take only half the item. For example, he finds a jewelry box which has weight greater than the knapsack. So it's not possible that he takes out some jewelry from the box and takes only half the box. Okay. There is another version of the same problem where that will be allowed, and we'll see how we can solve that later on. So for now, you can either pick an item or you have to leave it. So that's why this is called the 0-1 knapsack problem. Okay. He cannot take a fraction of the item. So now, before going into the mathematics of this problem, okay, what I want you to understand is that just become the thief for a little while. Okay, so think about, you are given, let's say, 4 items. Let's write down a problem. Let's put change this. So this is a problem at hand. There are 4 items, and the weights and the values are given. Okay, so now for example, for now I'll just change this weight later on. The maximum allowed weight that the thief can carry is 4. So this is a very small problem, so you can look at it, you can say, oh, if he picks up item number 2, then he gets a profit of 10 and weight is equal to 4. But instead, if he picks up item number 1 and 4, okay, then what is the profit he gets? If he picks up 1 and 4, he gets 18. Okay, so there are only two possibilities of weight. In this case, under 4, you can have either 4, or you can have 2 and 2, or you can also have, if I is equal to 3, you have a profit of 9. Obviously, this is the maximum, so this is the best choice. So, but this is not how we will do trying all permutations and combinations. Okay, so let me change the weight for now, just for explanation, to 5. So if the weight is 5, what are the possible combinations you will get? Okay, let's change it to 6. Let it be 6. You can get 1 and 2 item for a profit of 20. You can get 3 and 2 for a profit of 17. You can have 2 and 3 for 19. What other combination is possible? 1 and 4 is 18. Okay, so these are all the values. So obviously 20 is the highest. So we will go for that. Just a second, let me take this call. Hello? Okay, so there are different possibilities, but this is not the approach that you can take because the number of items can be more. Permutation combinations is not a good idea. Now, before we go into the mathematics, what we do is we look at the problem item by item. So when you start, say W is equal to 6. So as a thief, when you start to pick up an item, there are many things you have to keep in mind. What is the weight left in your sack? Okay. And what item you're picking, what is the value and what is the weight. So all of this has to be taken care of together. So at any point of time, you have the option of picking an item or leaving an item. So when you pick up an item, you have to make a decision whether taking this will be profitable, will it give me more value, will it fit my knapsack. If it fits and if it gives me more value, then I'll pick it. If it fits but it does not give me better value, then you can leave. So at any point you can either take the item or you can leave the item. Okay, so there are two options available to you. You have to evaluate these two options to see which one maximizes your value, and you have to be within your weight limit. So whatever items you have picked up, the sum of all the weights should be less than or equal to W, and your value should be maximized. Now, this problem is a bit complicated in the sense that since the weights differ, if you pick up item number 1 first, you will be left with W equal to 4. If you pick up 2, you will be left with W equal to 2. If you pick up 3, you'll be left with W equal to 3. Then with this 4, what you have already taken, and what can be possibly selected later on. Now what can be selected now depends on the current weight. It does not depend on this 6. Okay, so what we do is, again, it is a dynamic programming problem. If I tell you that I create a 2D array called VIW, which holds the value that has been generated by picking up items all the way up to ith item. I can be anything, 1, 2, 3, 4. So for ith item, and this weight, this is small w because this is the weight left. Okay. If this contains the value, if I already know for all the, because what I was trying to say is that when you pick up one item, the weight left is 4 or 3 or 2, because when you pair the weight with the items, there are you have I values are 1, 2, 3, 4. Okay, wi values can range from 1, 2, 3, 4, 5, 6. So at any point of time, whatever you have selected already can give you a resultant weight, even 0. What is left can be 2, 3, 4, 5, 6, right? So the I can take values from this to this, and W can take values from this to this. So when I create a 2D array with IW, I need to know the values in all the combinations of I and W. And I fill them up in a bottom-up fashion. I'll explain what that bottom-up means in case of Knapsack. Then only I can get the result properly. So let's go back to the so our problem formal description is given like this. You have items, n number of items. I ranges from 1 to n. Every item has a value associated. So you have, let's say for every item, you have the value stored in a single 1D array. We call it a tuple, is a pair of is values which you store like this. Mathematically, you represent all the values of the items from 1 to n as v1, v2, v3, so on up to vn. And the weights are also, so v1 weight is w1, v2 weight is w2 corresponding. And your w is greater than 0. So we wish to determine, this is the example that I took was for files. So just ignore this one. We want to find that subset such that you are maximizing the value, the sum of all the values of all the items that you have picked in the final. This is the final things that go in the bag. Subject to, this is the restriction. So this is the problem that is at hand. This is the limitation that we have to be within the limits of the weight. So it is an optimization problem. If we do brute force, that is again, like I said, you try all the pairs and see which pairs, not even pairs, all the subsets. So it can be a pair, it can be a 3 elements in that tuple, and you see what is the value and what is the weight, all the weights. If that tuple gives you a weight greater than W, then you discard that, and rest you see which one is maximum. Okay. So again, brute force will not help. Also, if you think of it as a divide and conquer problem, it will not help because you will again be repeatedly solving the same problems. We'll see why in a while. Okay, so we go for dynamic programming. And why we go for that? Because when you see, okay, let's go here. Okay, so if you look at this, I'll just go back to the previous slide. If you look at this here, what is the value if you have 0 items and you have some W weight available? If you had no items available and you still had some space in your knapsack, would that give you any value? You have nothing available and you have a sack, value is 0 because there's no item, right? And this W, small w, has to be between 0 and W's. Like I told you, the values W I can take is between 0 and W. Okay. Again, if by picking up an item, let's say the weight in your sack is, remaining weight is 5, and you pick up an item which has weight 6. So 5 is already there and you're putting in 6. So what is the weight left in the sack? It is -1, which is illegal value because your W is always greater than or equal to 0. So you can fill the sack to the brim, but you cannot have a -1. Okay. So in case, the second line says, in case the weight, this small w here, it is negative. When will it be negative? When you pick up something it does not have the capacity for. Then we say the value is -infinity. In the sense, why is it -infinity? If you saw in matrix multiplication, infinity, we initialized everything to infinity because that is the maximum value you can have, and you are trying to minimize, right? Here it is a maximization problem. We want to maximize the value. So what comparison do we keep? If you are getting -infinity, obviously it is not a maximum value, it is the least value possible. So to make this condition illegal, W less than or equal to 0, we put the value of, if you are going into negative weight, there is no profit because that's not possible for you to do. You put a -infinity there, just like we put infinity in the matrix multiplication problem. Now, okay, before I go here, just understand, just like in matrix multiplication, M1n was to hold the least number of multiplications for the matrix chain 1 to n. Similarly here, this is just a way of writing the 2D array sizes n and w, okay, like you see here. So the v, n and w, this will contain the maximum, again it's not, we're not talking about files, maximum profit that can be achieved by stealing a particular set of items. Okay, now just look at this equation here. Okay, if v gives you the value, if you have this I here is the item that you're picking. So let's say you start with 1, so you're picking up the first white item, and w is the weight that is left, or the current weight that you can see in the sack. There can be any possibility. W can range from 0 to capital W, the small w. So for any item I'll read the equation like this. For any item I given weight W, you have a choice to pick the item or to drop the item. Okay. If you pick the item, then we are talking about this. Okay. Let me just take it off here. If you pick the item, that means you are adding the value of the item, okay, to what is left of the problem. Now, if you picked up ith item, now you are left with I minus 1 items, okay, and what weight you are left with is the existing weight at the beginning of the problem minus the weight of this ith item. So if I picked up an item 4 with a weight of 2, okay, so I'll put the value of that item 4, then my problem will become the problem of having 3 items and a weight of 4 minus whatever the weight of the item, okay. Or if I plan to leave the item, this is the case where I leave the item. I somehow feel it is not the best item to pick. So what I will be left with is one less item and the same weight W. Okay. 11:30. Just a second. Yes, she's asked us. Go tell her to ask Papa for the password. Okay. So just a second. So if you have not understood this, let me know. I will explain it again. You can write in the chat box. Okay. So if you look at this, let's put it here. So the table I will make for this will be 4, 6. So this is the maximum value for 4 items with weight 6 allowed. If I apply the formula to this, if I decide to leave 4, I will be left with 3 items and a weight of 6. But if I decide to pick 4, I am adding, comma, I have 8 plus V of 3. Weight was 6, but the weight of item 4 is 2. Now, these are my two options. One option and two options. This is the option of leaving item 4, and this is the option of selecting item 4. So given these two options, I have to maximize the profit. So I want to find the maximum of the two. Now, if you look at the equation, to find 4, 6, I need 3, 6 and 3, 2, right? I don't have 3, 6 and 3, 2, okay? So before calculating 4, 6, I need 3, 6 and 3, 2. It could have been 3, 5 and, it could have been 3, 6 and 3, 1, depending on the weight of item number 4. So if the total weight was 6, item number 4 could have weight 1, 2, 3, 4, 5, even 6, and it could even be 7. So if it was 7, I would get, in this case where you pick the item, I would get V of 3 minus 1, which would be illegal in my case. If it was 6, I would get V of 3, 0 here for this one. If it was 5, I would get V of 3, 1. If it was 4, I would get V of 3, 2. Again, if it was 3, I would get V of 3, 3. So what I'm getting on the right hand side right now might not be the same. It depends on the weight of the item. So to calculate 4, 6, I might need 3, 0, 3, 1, 3, 2, 3, 3, 3, 4. With respect to the 2D array, I just erase this. If I make this 2D array that we are talking of, one, two, three, four, five, six. 1, 2, 3, 4. I'm saying that my 4, 6 is the maximum value that I'm getting. This is what I'm trying to calculate. But if you see, 4, 6 gives rise to 3, 6 and 3, 2. And it could possibly, like I mentioned, it could give rise to 3 minus 1 is illegal. 3, 0, it could give rise to 3, 0. I haven't written the 0 column, so 31, 32, 33, 34, 35, 36. Okay, that means for doing this calculation here, I need this row already prepared for me or ready, because then I have used these values to get this value here. Okay, if you see, okay, similarly, when you have, if it was V of 3, 6, suppose I want to calculate this now, this will be 2 something, right? So I'll need this column first. If I'm calculating V of 2 something, I would need V of 1 something. So I have to calculate the first, not the column, the first row. So that means to calculate the fourth row, I need the third row. To calculate the third row, I need the second row. To calculate the second row, I need the first row. So my bottom-up approach should start from the first row. So I have to do row-wise calculation. Just like in matrix multiplication, we saw to get the pairs of length 2, 3, 4, we have to do the calculation diagonally. So here the dependency is such that you have to do the calculation row by row. Okay. So if you look at this, your bottom problem is when you have no item and you have all the possible weights. When you have no item, any weight that is available, your value is going to be 0. Okay. When you have an item and all the available weights, if I give you one item which is within the weight limit W, I can pick it up only when this column allows me. My small w should not become less than -1. Okay, I think we'll do that with an example. But what I want you to understand is that when we are trying to maximize the profit, if I start with item number 4, I have to maximize the profit for 4 items with given this weight. I decide to pick or leave the item. Based on that, I am left with 3 items and a particular weight. That weight can be anything. That's why you see in this table, weight takes all the values from 0 to W. Because when I pick an item, its weight will decide where this will go from 0 to W. And if its weight is greater than this capital W, then you will get a negative weight, which is illegal. So that is not considered, obviously. If the weight is within this range, you will get a sub problem with 3 items and this weight left. Okay. So okay, I'll change this text here. I actually forgot to change because we are doing it for Knapsack. So what we are trying to do, we want to find VIW to store the maximum profit for the subset of files is the subset of items that you select for size at most W, which is the weight. It's a similar problem, but the nomenclature is different. So if we can compute all the entries of this array, then this will have the maximum of all the possible solutions. So what are our initial conditions? If you have no item and you have any weight possible given to you in the knapsack, your value is going to be 0. And if you have items and the weight that is left in the sack and the weight of your item, if you subtract the two, if you get any negative value. So if picking up an item basically overloads your sack, then you give a minus in. So it's not a maximum value. It's like an impossible value to get. So that's why we put a minus infinity. Then we calculate for any item, we calculate. Why are we giving initial settings here? Because we have to do the calculation in a bottom-up manner, like I told you on the whiteboard, because of the values you're getting on the right-hand side. So for doing the first row calculation, you'll need the 0th row values here, these, okay? And this also you'll encounter, okay? So your higher value is dependent on the lower value here and here. Depending on whether you pick or leave the item, you will have to add the value of the item. If you're leaving, no need to add the value, just do I minus 1 W. If you're picking, add the value to I minus 1 W minus W I. So I ranges from 1 to N and your weight ranges from 0 to W. So VIW is maximum of the two options you have of leaving the item or picking the item. So overall, you will decide how, when you had, if this I is 4, you will have 3 items on the right hand side. How did you pick those 3 items? Again, you have to do maximum of picking. So this, you will see that this will give you all the combinations possible, and you're storing the values in a table, so you'll not have to repeat your calculations. We'll see when we do an example. Okay, so for item 0 and weight W is 0 for all of this, and for this calculation is to be done row by row. So that is the bottom up computation. It depends on the problem. For matrix, because we had to do the matrix pairs and length of 3 for the chain and 4, we were doing like this in the 2D array. This time we are going to do the calculations like this. Okay, that is your bottom up. There the bottom up was doing the diagonal calculation. Okay, so let's do the problem tomorrow. I think that's it. I think we took for 1 hour already. Do you have another class after this, Amandeep?
No, mom.
You want to continue or you want to stop?
Mom.
You can be
I
honest.
don't know.
I don't know. You can't decide for the class.
Yes, mom.
नहीं तो मार पिटेगी. Okay, let's stop here. So what I would suggest is, again, I have to make some changes in this presentation because of this. I did overlook this. I just took a screenshot of this part. So just go through matrix multiplication again. I'll just send you a screenshot of some matrix multiplication problem. Just send it to the class on WhatsApp. Just send it to the class for practice. Okay.
Okay.
Uh,
Okay.
so that if you have any issues in that, then we can discuss it before doing the knapsack problem. Okay, and I'll inform you tomorrow morning if I will take class tomorrow or not. Okay, I am not sure. I have did you take the attendance?
Yes, mom.
Okay, all right. Thank you.
Thank you.
Bye.